Okay, so here's an interesting topic, optical activity. Now, it turns out that this is one of the few things I would say in organic chemistry that doesn't tie back to what are the electrons going to do, right? Because that's the main question in organic chemistry. What are the electrons going to do? But optical activity is a really cool tool, or a really cool aspect of nature, I should say, that enables us to measure things in a sophisticated way. So let's look at this. Enantiomers have opposite configurations, R and S. We talked about that before. And listen, they rotate plane polarized light in opposite directions. Okay? So let me tell you something that you may have learned from a physics class. We don't need to get to understand it very deeply, but this is how light works. Okay? So as light is propagating in a particular direction, so let's call this the direction of propagation, okay? So light is going in this direction. As it's going in this direction, of course, it's made up of little tiny photons, right? Which are massless. So that's how small they are, right? It's made up of photons. They actually have an amplitude that of an electric field that goes in this direction, which is signified here by the red, okay? They have an electric field that has an amplitude that goes in that direction, the wavelength of which is characteristic of the light itself. For example, the visible light is between 400 and 900 nanometers. Okay, so and in the there's a corresponding magnetic field which has an amplitude, right, which is signified by the blue. Okay, so we're not going to measure this. It's just important that you know that light has such a feature. All right. Now, if you take a polarizer, and that is a disc here with slits in it, okay? So if you take a disc with slits in it, the light, whereas light that's coming, say, from the sun, has amplitudes in all directions, okay? But as it goes through the polarizer, it filters all the light except the light just going straight up and down. Okay, can you see that? That's what we mean by plane polarized light. That is light that's been divided up into particular planes. Okay, so if it's going through here and it's going like that, and it hits this next polarizer, it goes right through because it's in the same plane. Okay, however, if this goes through here like this, and then you turn this polarizer 90 degrees, it won't go through because it's rotated in the opposite direction. Okay, this is called plane polarized light. Polarized sunglasses do this. I mean, the polarized sunglasses do this here, but they basically make it so that a lot less light gets through the lens. All right, so now it turns out this is very interesting. Compounds that can rotate plane polarized light are called optically active. What do you mean rotate plane polarized light? Well, they actually act like this lens right here, this polarizer. Or rather, I should say, they act like that lens, except when the light comes through, it's rotated. So I think my next slide shows that. Okay, so watch this. As light comes through, here's your light source. Okay, let me go back to red. It comes through and it gets polarized into a plane, right? Well, while it goes through the sample, there's a sample inside here. Can you see how that arrow, which is the direction of its plane, its polarization, it gets turned? Can you see that? Weird. Amazing. Okay? We in this class are not going to understand how that happens. We're only going to know that it does happen. All right? So, again, light comes to a light source. It goes through a polarizer. My slide's getting pretty ugly here. It goes through a polarizer, and it's polarized up and down, up and down, up and down, up and down. And then as it comes through the sample, it starts to turn. Can you see that? Like that. Boom. Okay? So the amount that it gets turned is called its called its rotation. Okay? Of course. Sorry. It's early in the morning. All right. I use that excuse at night too, don't I? I say it's late at night. I can't think of any of the vocabulary. All right. So that means that, or that is a feature of optically active material that we are going to use, okay, in our analysis. All right, so enantiomers will rotate the plane. This is sort of just a review of what I said. Enantiomers will rotate the plane of the light to equal degrees, but in opposite directions, right? So if the R isomer goes, let's say, I think in my next slide, it's like 23.1 degrees plus, it rotates it, say, clockwise, 23.1 degrees. Can you guess what the S is going to do? It's going to go in the minus direction, 23.1 degrees. Okay? The degree to which the light is rotated depends on the sample concentration. That is, the greater concentration you have of the stuff that you're analyzing, and it also goes through the length through which you allow the light to pass through the sample. All right? So a standard optical rotation measurements are taken with 1 gram and are dissolved in 1 milliliter of solution with a path length of 1 decimeter for the light. All right? So it's 1 gram per 1 milliliter is the concentration, and 1 decimeter of length for the light. So it's not important that you remember this, okay? It's just important that you remember those particular details. It's just important that you appreciate that we have some way of really dealing with this, okay? This is not just magic. It's not a black box. All right, so having said that, the temperature and the wavelength also have an effect on the rotation and have to be reported with the specific rotation, okay? That's our notation. That's for how we report the stuff. All right, so consider the enantiomers of 2-bromobutane, right? Remember these, right? I got it backwards, by the way, in that previous example, but either way, so the R, it looks like it goes through at 2-bromobutane, and its specific rotation is negative 23.1. All right, that's at 20 degrees Celsius, okay? If that's true, then the S is going to be positive 23.1, right? Okay, and I'm going to give you a little preview of the next slide. A racemic mixture means that it's 50-50. So if we make this stuff through some method that doesn't specify which we get an R or an S, we're going to have 50-50. In which case, our specific rotation of that is going to be 0, right? Can you see why? Because it would be the average of the two. All right? So plus and minus signs refer to the direction of the plane the light is rotated. All right, and it's a term which we will see. If it's a plus rotation, it's called dextro-rotatory, and if it's minus, it's called levo-rotatory, okay? Plus is dextro, and I remember that by putting, look, that X looks like a little plus sign. Dextro-rotatory and levo-rotatory is the minus, all right? So the compound below has the S configuration. Its optical activity at 20 degrees Celsius is levorotatory, it's minus. At 100 degrees Celsius, it's dextrorotatory, it's plus. Okay, look it. There is no correlation between R and S and plus and minus. So that's going to, you all are looking for trends, as you should be, and correlations and tricks, as you should be. But there is no trick here. It's simply not something we can predict. All right. So the magnitude and direction of the optical rotation cannot be predicted and has to be measured experimentally. We measure it experimentally, and then we write it down in a book, right? We say, okay, so the optical rotation at 21. We measure the temperature in the lab at 21 degrees Celsius, and the wavelength of light we use, let's say 550 nanometers, okay? And that's how we report, is equal to, right? Is equal to, let's say, 44 degrees Celsius. That would be a lot. However, we can, so while we have to measure it experimentally, we can predict the rotation of a racemic mixture to be 0, right? Because it's 50-50, all right? So the optical rotation of each enantiomer cancels each other, of course. A racemic mixture, as I said on a previous slide, is a 50-50 mixture of the two enantiomers. Now, if you have an excess of one of the enantiomers relative to the other, the mixture will have an optical rotation. For example, if we have 1% of the R and 99% of the S, we can expect it's going to pretty much be like the S, right? So we would have an enantiomeric excess of 98%. Can you see that? The EE would be 98% if we had 99S and 1% R. if one enantiomer is present in excess relative to the other, the mixture is going to have an optical rotation, but it'll be less than the pure enantiomer. Let's figure out how to, let me show you how to calculate the enantiomeric excess. So an enantiomeric excess, which we call percent %EE, okay, is can be determined by the following. Suppose the mixture, here's the formula. You can do it yourself. Okay, suppose the mixture of R and S has a specific rotation of negative 4.6. Then we would say it's 4.6 up here, and it's negative 23 down here of the pure enantiomer, right? And so we would see that the enantiomeric excess is 20%. All right.